Today we will discuss the pressure measuring devices. Myself, Professor Piyush Joshi, working as an assistant professor in Chemical Engineering Department of KK Wag Institute of Engineering Education and Research, Nasik. I welcome you all in this video. Let us now discuss what we mean by pressure. If we consider when a gas or a liquid is contained within a closed container, their molecules are in constant but random motion. They are constantly colliding with each other as well as with the wall of containers. All of these collisions occur over a given area combined to result in a force. This force over a defined area is referred to as pressure, and therefore the pressure is given by force per unit area. So if we write down mathematically, P is given by F upon A, where P is pressure, F is force, and A is area. If we consider the Pascal's law given by Blaise Pascal in around 1600 century, he developed his principle of transmission of fluid pressure, and this principle is known as Pascal's law. This law states that the change in the pressure within a closed container will be conveyed equally in all directions within the container. Therefore, the pressure within the container can be measured from any point within the container. So that Pascal's law is a common basis for all the measurement principles for measurement of pressure. Let us now discuss the unit of pressure. The basic unit of pressure in SI unit is Pascal. The Pascal is defined as a force of 1 Newton per square meter, and that is 1 Pascal is equal to 1 Newton per meter square. The standard unit of measure in English system is pound per square inch. It is generally abbreviated as PSI. In MKS system, the standard unit is kilograms per square meter, that is kg per meter square. The units used for pressure for high pressure measurement is as shown here: 1 Newton per meter square, that is 1 Pascal. 1 atmosphere is equal to 14.696 psi, that is pound per square inch, and that is equal to 101.325 kilopascal. For low pressure measurement, the following units can be used. The first one is the 1 millibar, that is equal to 100 dyne per centimeter square. And if we converted it to the pound per square inch, it become 14.4 into 10 raised to power minus 3 pound per square inch. That is nothing but PSI. The second unit that can be used is the micron. 1 micron is equal to 10 raised to power minus 6 mm of mercury, and that is equal to 19.34 into 10 raised to power minus 6 pound per square inch. The next unit we can use for measurement of low pressure is torr, and 1 torr is equal to 1 mm of Hg, and it is equivalent to 19.34 into 10 raised to power minus 3 pound per square inch. So these are some units that can be used for measurement of pressure. If we consider the importance of pressure measurement in process industries, the pressure change the different characteristics of the material that involved in a chemical process plant. So the proper monitoring and measurement, or we can say the pressure measurement and its control, is very much importance in the process industries. Another day-to-day example, if we taken, the tire pressure available in the vehicles is also important, so that we can achieve the uh, good performance of the vehicles. Another important day-to-day life example is nothing but the human body blood pressure. So if that blood pressure of human body is in prescribed limit, then it is okay, or otherwise we have to take care of our health. So these are few examples or importance of pressure measurement we can describe here. In industry, the different reference can be taken for measurement of pressure. Let us now discuss the first one is the gauge pressure. In gauge pressure, we use the ambient atmospheric pressure as the reference point. The gauge pressure transmitters have a small reference port to sample the ambient, that is the atmospheric pressure. The second reference pressure used in industry is the absolute pressure. In absolute pressure, we use the perfect vacuum pressure, that is the absolute zero, as shown in this particular figure at the bottom line. All the absolute pressure measurements are usually positive. Next reference pressure is vacuum pressure. The pressure between the atmospheric pressure, that is shown by this dotted line, and the absolute zero, that is the bottom line I am highlighting out here, is nothing but the vacuum pressure. The standard defined reference is usually absolute zero pressure, shown at the bottom line, shown by the bottom line in this particular figure. The gauge pressure, absolute pressure and atmospheric pressure is abbreviated here. The pressure usually positive above atmosphere is usually called as a gauge pressure. The convenient unit for measurement of gauge pressure is pound per square inch, PSIG. The pressure below atmosphere in vacuum is usually called as negative gauge pressure. The absolute pressure is measured from a perfect vacuum and it is in a PSIA unit. Absolute pressure is determined as algebraic sum of the readings of a barometer and that of on a manometer showing the gauge pressure. Manometers which measure the absolute pressure are also available. These manometer measure the pressure with reference to the absolute zero pressure. The differential pressure has no reference to either the absolute vacuum or atmospheric pressure. So we know the differential pressure is nothing but the difference between two legs of manometer, and it is P2 minus P1, and that is the value we are obtaining by using the differential pressure measures. Let us now discuss the pressure measuring instruments. The pressure measuring devices are usually classified as follows. The manometers, further classified as barometer, U-tube manometer, well manometer, inclined leg manometer, and enlarged leg manometer. The second category in pressure measuring device is of elastic elements. The first elastic element is Burden tube. Second is the use of corrugated diaphragms. Third is use of capsules. Fourth one is the use of bellows. The other important measuring devices are the pressure transducers. Which transducers we know, the transducer convert the pressure into the relatively convenient way so that we can measure the pressure very easily. So the pressure transducers are first one of the resistance type, next is the inductance type. It is usually called as LVDT. LVDT stands for linear variable differential transformer. Next is the variable reluctance transducer. Another type is variable capacitance type of pressure transducer. Next one is the solid state pressure transducer, and last one is the thin film pressure transducer. So these are some different pressure measuring devices and transducers that we can use for pressure measurements. The range of instruments is as shown in this particular PPT. The high pressure, usually 1000 atmosphere and above pressure, is usually measured by electrical resistance type of pressure measuring devices. On the other hand, the high vacuum, that is up to 10 raised to power minus 9 torr, it can be measured by using the McLeod gauge, thermal conductivity gauge, and ionization gauge. The moderate pressure between 1 mm of Hg to 1000 atmosphere can be measured by the following instruments. We can use in this range the Burden tube, diaphragm gauge, and bellows for measuring the pressure in the range of 1 mm of Hg to 1000 atmospheric pressure. And below 1 mm of Hg, that is low pressure, we can use the manometers and low pressure gauges for the measurement of pressure. So this range of instruments can be useful when we have to apply the suitable pressure measuring instrument in industry. Let us now discuss the liquid column manometer. The manometer is a device used to measure the pressure at a single or multiple points in a single or multiple pipelines by balancing the fluid column by the same or another column of the fluid. Manometers can be categorized into two types, namely the simple manometer and another is the differential manometer. Simple manometric devices measures pressure at a single point in a fluid, whereas on the other hand, differential manometric devices measure pressure at two or more number of points in a single or multiple flow lines. The simplest type of manometer is the simple manometer, wherein we have three types of simple manometers like piezometer, U-tube manometer, and single column or micro manometer. The simple manometer consists of a glass tube, straight or bent, whose one end is connected to the point at which the measurement of pressure is required and another end is left open to the atmosphere. So the U-tube manometer is look like as shown in this figure. We can either keep one end of the manometer, one leg of the manometer open to atmosphere, or we can connect it to the second point of application in a single line or multiple lines. And the another leg is already connected to the pressure measuring point where we need to measure the pressure. So the P2 can be atmospheric and P1 can be the actual point of measurement. This manometer consists of U-tube as shown in this figure, in which the manometric fluids can be used. The manometric fluids would be water, mercury, and any other liquids can be used. The advantage of using these fluids is that the mass density of this fluid can be obtained easily and they do not stick to the tube. That is why water and mercury are the famous one. Mercury is nowadays not much famous because of its toxic effects. The pressure is read out by measuring the height difference between two legs and it is given by H. Then we can calculate the pressure by using rho g into H. If we use the U-tube manometer to find out the differential pressure, if the P1 is greater than P2 as shown here, P1 is greater than P2, then the differential pressure, that is P1 minus P2, is obtained by simply the multiplication of rho g into h, where h is the difference difference of manometric liquid height in the manometric legs, where P is the mass density of the fluid, G is gravity, and P1 is unknown pressure, and P2 is the atmospheric or some another unknown pressure. Next is the liquid column manometer. For amplifying the deflection in the liquid column manometer, liquids with lower density could be used, or one of the limbs of the manometer may be inclined. And this is generally called as inclined leg manometer. By inclination given to the one of the manometric leg, we can amplify the strength of the signal we are received in the liquid column manometers. Commonly used manometric liquids are mercury, water, or alcohol. Some of the important and desirable properties of the manometric liquids are as follows. They should be highly chemical stable are preferred. Second is the low viscosity manometric liquids can be preferred. They should have the low capillary constant. Also, the manometric liquids with low coefficient of thermal expansion would be preferred so as to minimize the ambient temperature effect on the pressure measurement. Next, important characteristic of the manometric liquid is they should be low volatile, so that there should not be vaporization of the manometric liquids if application is in the high temperature region, and they should have the low vapor pressure. So these are some important and desirable properties of the manometric liquids are considered. High thermal stability and low volatility are important for maintaining a constant specific gravity. High viscosity causes the transmission lag. The thermal expansion causes changes in zero reading. While measuring the low pressures, vapor pressure of the manometric fluid is an important consideration. The properties of some of the commonly used fluids are given on the table on next slide. So these are some important characteristics of manometric liquid are given. In the first column, I have mentioned the different fluids that can be used as a manometric liquid: methanol, ethanol, mercury, toluene, and carbon tetrachloride. The specific gravity is shown in the second column. The boiling point at 760 mm of Hg, that is the atmospheric pressure, is given over here. Their surface tension in dyne per centimeter is also mentioned in the fourth column. The viscosity of fluid is also important characteristic. So the fifth column shows the viscosity of different manometric liquids as shown in this table. And the last column shows the coefficient of volumetric expansion in the last column. So these are few usually used manometric liquids, of which the different important characteristics are mentioned here. The liquid column manometers, if we consider the advantages, they are simple and cheap. High accuracy and sensitivity can be obtained if the manometric fluid is chosen properly. Availability of a wide range of filling fluids of varying specific gravity can be possible. The response of the liquid column manometer is linear, and most important advantage, no frequent calibration is required for the liquid column manometers. On the other hand, the liquid column manometer has certain disadvantages also. The disadvantages are as follows. They are sensitive to the temperature change, and if they are volatile, the manometric liquid will show the different zero readings. They are not suitable for sterile application as they are in direct contact with the pressure measuring nodes. And for sterile application, the liquid column manometers are not feasible. By using the liquid column manometer in sterile application will lead to the introduction of the impurities. Next disadvantage, they are unsuitable for measuring the fluctuating pressures, because at each fluctuation in pressure we have to measure the height difference in the manometric legs, and that is why the liquid column manometers are not suitable for the fluctuating pressure conditions. Next type of manometer is a well type manometer. In well type manometer, one leg is replaced by large diameter well of that the U-tube manometer. Since the cross section area of the well is much larger than the leg, when pressure is applied to the well, the manometer liquid in the well lowers only slightly compared to the liquid rise in the another leg. So by using well type manometer, we can achieve the amplification principle by using the large quantity of the manometric liquid. As a result of this, the pressure difference can be indicated only by the height of liquid column in a single leg. As shown in the figure, the yellow is the manometric liquid, and this is the point where we can apply pressure, and due to this application of this pressure, this manometric liquid rises in the single manometric leg, and we can measure on a scale where we initially mark the zero reference line. Here, if we want to measure the differential pressure, that can also be possible. The differential pressure here is given by P2 minus P1 equal to rho into bracket 1 plus A1 by A2 into H, where A1 is the area of small diameter leg and A2 is the area of well. If A1 upon A2 is far less than 1, then P2 minus P1 is directly equal to the rho into H. So we are neglecting this term here. If the area of well is 500 or more times larger than the area of vertical leg, the error involved in the neglecting the area term is negligible. Another type of enlarged leg manometer can also be possible. It is quietly similar to that of the well type manometer. In enlarged leg manometer, the vertical leg is also somewhat enlarged, and in this construction we can use the float and Pointer assembly to show the differential pressure on a calibrated scale. So change in height is directly shown by the relative movement of the float onto the surface of the manometric liquid, and it can show directly the differential pressure on a pressure dial. Another important manometer that we can use is the inclined leg manometer. As shown in the figure, the inclined leg manometer can be used for obtaining amplification of the reading of the applied pressure, and here the change in height of the manometric liquid is given by H upon L is equal to sin theta, or we can have the height H, rise of manometric liquid in a manometric leg, is given by L into sin theta. Rest of the things are same for pressure measurement. If you like this video, please like, share and subscribe. Thank you. Thank you very much.